Every day, thousands of medical samples are collected in hospitals across the UK. These samples are typically processed in a centralised hospital laboratory, and transportation is required from the wards to the lab. Pneumatic tube systems and line-guided vehicles are highly efficient systems used to transport samples, but they are expensive and inflexible. Where minor and urgent transports are required, nurses or lab staff are often drawn from their posts, wasting precious time that they could be spending with patients. We propose a mobile robot that can be deployed in hospitals and temporary clinics to handle these transport tasks. Pickups can be requested through our online portal, and the robot can autonomously navigate to its destination, replanning its path on the fly when obstacles are detected.
The robot chassis is primarily built from ABS plastic sheets with an aluminium structural frame. It consists of a wheeled base, an upper cabinet for payload and electrical components, and a top-mounted manipulator arm for interfacing elevator panels. The two driving motors form a differential-style locomotion with caster wheels front and rear for stability. The payload cabinet contains the specimen to be carried, and the side door is secured using a set of solenoid locks. Between the upper and lower sections sits a rotating laser rangefinder or a LiDAR sensor, which is used for navigation and mapping. Power is supplied by lithium-ion batteries and distributed throughout the robot as required. Electrical components are mounted to a set of racks that can easily be removed to facilitate practical service and maintenance. On top of the robot, an RRP manipulator acts as the robot's finger for reaching out and pressing buttons to autonomously open doors and operate elevators. The arm is guided by depth camera.
As part of the robot's initial deployment, the environment is mapped into an occupancy grid by having the robot moved around and taking readings from its sensors. This method allows for an effective localization of the robot and a feasible path planned for the robot to navigate to its desired destination. The robot is localized using an adaptive particle filter, where each particle represents a potential pose of the robot. The estimates are evaluated by comparing sensor readings to the known map, with poor matches being removed while accurate ones are carried forward. Thus, the particles converge on the robot's true location as it moves around. A path to any destination in a map that avoids all obstacles is achieved using the real-time RRT-star algorithm, which grows the tree covering the environment, where the branches of the tree represent possible routes the robot can take. This tree is maintained continuously and rewired as new obstacles are added or removed in the course map when detected by sensors, enabling dynamic obstacle avoidance. Initial testing using the Turtlebot platform has shown that the navigation subsystem can successfully map and localize itself within its surroundings and produce a route that can be altered on the fly to avoid temporary obstacles such as passerby. This navigation system was developed to be capable of dealing with the ever-changing and dynamic hospital environments.
To move between floors, image processing in the form of template matching is used. With the top-mounted depth camera, a picture of the button panel is taken. Templates corresponding to the available floor numbers are stored in the robot's memory, and the desired one is applied to the image to look for a match. Once the correct button is identified within the image, the related depth map is examined to find the real-world coordinates of the pixels. The coordinates are passed to an RRP manipulator, which then reaches out and presses the button to operate the elevator.
Medical staff can order a pickup through a web interface. After logging in with credentials, pickup jobs can be scheduled or deleted as required. When creating jobs, they are categorized as low or high priority, with the robot carrying out high priority jobs immediately. When no high priority jobs are waiting, the robot makes rounds connecting the specimens until the compartment is full before returning to the lab. The updates on the status of scheduled jobs can also be viewed via the web interface. When the robot arrives, the door can be opened by staff members by scanning an RFID tag to access the compartment.
The developed system poses many benefits, such as relieving nurses of transport duties, enhanced patient care, improved employee and customer satisfaction, and cost savings. On behalf of Team 9, thanks for watching.